Greetings, everybody. We are back for the autumn semester of our Guelph Physics live stream. Geez, has been, I'm glad to see we've actually got some viewers. I was nervous with back to school. I didn't know how many of you were actually going to attend tonight, but this is exciting to see that there's people here waiting for us. And we have an exciting opportunity this evening to talk to an experimental nuclear physicist here from our very own department. But I guess I might as well start this off as always. Welcome. Citizens and scientists from this great big weird wild and wonderful world in which we live. I, as always, am your humble science communicator, the Great Orbax, joining you here from Physics Hollywood at the University of Guelph. Yes, that's right. We've moved from our previous location of Physics Hollywood to a brand new one, which any longtime viewers would know brings with it all types of inherent difficulties on its own. So hopefully things run as smooth as they possibly can this evening. I also want to point out that we'll be asking questions from of our guest. So if you have the opportunity to ask questions or you have any questions that you're curious about, you can post them in the chat and we'll bring them right up on the screen. I can give you an example of this right now. Look at this. People are already saying hello. Hello, Samantha. It's good to see you. Glad you could join us this evening. Yeah. This is, it's exciting. We're all back to school here at the University of Guelph. Fall semester is full upon us. We're a few weeks in now, and as it would have it, it's a good evening to have a nice little chat about some nuclear physics. Now, our guest this evening is an assistant professor here at the Department of Physics at the University of Guelph. He's joining us all the way over from the McNaughton building. So approximately 40 meters in that direction on a straight line tangent, but you could possibly be able to see where I'm shooting from in his window. Joining us this evening is Dr. Dennis Muecher. Let's bring him in, Saction.
Hello, Great Orbax.
Hello, how are you?
Thank you for having me. Let me turn around and see if I can see you. Good to see you. Thank you for having me. That's exciting.
Yeah, not a problem.
It's so nice to be back in person on campus, teaching to people live as opposed to Zoom. So it's too bad we have to do this on Zoom tonight. Hopefully someday we can go back live and have everyone in the lecture hall or wherever and talk in person. But
now, are you teaching?
Thanks for setting this up.
No problem. Are you teaching this semester?
I am teaching. I'm teaching IPS 1500, which is a course Integrated Mathematics and Physics for first-year students. And I really, really love that course. I love teaching first-year students. They are excited to be here. And despite that, I am teaching physics. I mean, physics is not everyone's piece of cake, right?
Absolutely.
But actually, most people, I think, enjoy it. And I certainly enjoy it. So it's great. And actually, so we do kind of a hybrid thing. I am teaching face-to-face in class, but if people really don't feel comfortable coming on campus, I also have a Zoom session running at the same time. So they can join the lecture through Zoom. But actually, I find that, say, almost everyone comes really in person. That's really great. It's so much more fun. People can talk to each other, meet each other. You have like new friendships coming up. It's just more interactive, more fun.
Well, that's kind of a huge part, I think, of what we've all sort of experienced over the last year is that the social aspect and the social element of teaching and learning was a huge loss over this last year, and that now that we can finally get back together and kind of do this, I think those friendships and those bonds that are being made are vitally important for some of our students.
Absolutely, absolutely. I think it's also from a research perspective, just having meetings again in person is so much more productive and fun. And they just run longer. I don't know why. Like a Zoom session with my grad students would maybe only last half an hour. And now we're just here over coffee and we talk and we chat and we come up with new ideas. And it's just more fun.
I guess it's harder for your grad students to shake you loose now when you're actually face to face.
It is.
But let's get into
doing this hybrid. You know, we're still trying to minimize. Like if it's not really necessary, then we try not to meet. I mean, COVID is still there.
Sure. Yeah, so absolutely.
Please, people, get your shot. Right? Please get your shots.
Absolutely,
so
and it's important. It's important to stay vigilant at this point too. It's easy to
Yes.
get lulled into a false sense of safety, but positivity is on the horizon, and it's interesting. I
Yeah.
really wanted to discuss with you tonight. We have so you're an experimental nuclear physicist.
That's right.
You work with this idea of sort of searching for how the elements have been formed. You also work with this idea of taking nuclear physics and applying it in different ways to create novel
Right.
cancer treatments. And it's an interesting mix of stuff that we've tackled previously in this series. We've talked about medical physics. We've talked about this idea of searching for these, the origins of these heavier elements. To bring these two together is a really unique and novel idea. So I wanted to start this off before we get into your history with physics, before we get into what you do. I'd like to open with this question. And the question is this: if you were to tell somebody about the most exciting thing about your research, what would it be?
Okay. Oh, that's a very hard question. The most exciting thing for me personally is that I'm really interested in the things I am allowed to study, like the questions that we are trying to answer. Like one of the questions, for example, would be, where do the elements come from in the universe? Right. So we know they are kind of baked in stars and things, but how does that work in detail? I find that a very fascinating question, and I find that very motivating to wake up in the morning and be able to go to work and think about these kind of questions, but also then applying these things to things which might be beneficial for the society later. I find that also extremely fascinating and just fun. Yeah. So that's what I love about my research. It's just exciting to work on these topics which are interesting to me personally.
Well,
So that's really cool.
It is really cool. And I think, we have a lot of undergraduate students who tune into this. And I think when you're studying physics at an undergraduate level, or even at a graduate level, it can be difficult to sort of envision where your career is going to go. So
absolutely. Yeah.
So where did you start? How did you get to this point? Was it always this kind of interest in these varied things and then bringing them together? Or did you just kind of naturally get to this place?
Actually, I am one of these lucky people who kind of made their hobby to become their job. I always was a amateur astronomer as a high school kid.
Okay.
So I was always interested in stars and stuff. So I started to read some books, like popular science books. I was reading about black holes and things like that. It was super interesting. And then one day I decided I want to have a telescope. So I went to a store and bought a telescope. And then only later I figured out that telescope was actually not the one I needed. So I actually brought it back to the store and said, hey, you sold me something which is not good. So that's how all that started. I did then more reading, and I actually still have my first, it's a German book. Let me show you anyway.
Yeah, get it. It's exciting.
That was my first physics book I ever bought. That is a book for amateur astronomy where you learn, like, how does a telescope work? How do I set it up? And so on. And I spent hours outside just watching the stars and trying to figure out where are the planets and why are they there and what's a galaxy and things like that. So I got really interested in that. And then I told my parents that I want to become an astronomer, an astrophysicist. And they started laughing at me and said, well, you can't get a job like that. That's impossible, right? There's no job. So actually my dad, he picked the newspaper of that day where you have all these job advertisements at the back. And he showed me, like, do you see any advertisement here for a physicist position? There's no job, right?
That's not very encouraging.
No, my parents are the most supportive people for my job. Thank you very much, Mom and Dad, for allowing me to study this. But I think they just got a little bit scared at that point to say, like, an astrophysicist, what is that? What is that person doing? So I think my message to the young people out there is, if you enjoy something, go after it, even if it sounds like unlikely that you will ever make it. Just give it your best shot. It's so important to do something which you really like, and you spend so much time with your work and so much time with the people you were working with. So that's really important.
Absolutely.
So it worked out. Right?
Absolutely. I think it's one of those things too that, when we speak with students, people get so bogged down in this idea that they have to find a job afterwards. And my advice, people throw out this advice, this idea of always follow your passion. And that's not necessarily entirely true. It's more along the lines of find something that you enjoy doing and that you can see yourself doing every day, because there's work involved in it, you know, to get kind of where you want to go with those types of things. But it's, if the work can be its own reward, if it's stuff that you like
passion
to
helps,
do,
right? Yeah, passion helps you to keep doing what you like to do, to get better, and just time will bring you forward and make you stronger, and you can reach your goals, right? I think this is, just go for it. So yeah, I started as an amateur astronomer, and then I decided to study physics. And so then that was, of course, much broader, and I somehow ended up in nuclear physics, and then actually learned how closely that's connected to astronomy and astrophysics.
Okay, well, like, did you know that was the case, or did it just kind of, because you know, I'm talking to you and I'm hearing you start out as you want to be an amateur astronomer, then you fall into nuclear physics, then you get into medical physics later. How is this all connected?
Yeah, that's a very good question. No, I did know that there is this connection. I knew that a star is so hot inside that most things are more dictated by nuclear physics than by chemistry or something. So I was aware of that. I didn't know, like, all this fascinating research that we do, that there's so much going on the level of nuclear physics, which is directly connected to nuclear astrophysics. I wasn't quite aware of that. And that's also just something which involved a lot more over the last decades, with things like these radioactive beam facilities we can talk about later, where you can study things you couldn't study some decades ago. So that was really interesting for me to figure it out. So the medical physics, I always was also interested in that medical field. Or actually, after my PhD, I worked in a hospital for a while as a medical physicist, doing treatment planning for radiation therapy in a radiation therapy facility. And I found that also very rewarding, because I could immediately see how that's beneficial to people. And I found that so motivating to wake up in the morning and say, there's people waiting for you to go to work to do something useful. I found that fascinating. And then later I had the opportunity to combine these two things, to do research, but also to be involved in the medical field. And then that's very cool. And yeah, surprisingly, there is this strong connection between nuclear physics and medical physics. I mean, it has always been there. Like, so many things which are now used in medical physics have been discovered in physics, like such as X-rays or other imaging techniques, like a CT scanner or a PET scanner, wherever you are involved with radioisotopes. There's this very close connection to nuclear physics, specifically nuclear physics. Or physics in general. I mean, there is this very strong link between physics and medicine. So now I'm making use of that. And so the kind of the same techniques we are using for our nuclear physics research turn out to be also very useful for medical physics. So it somehow more or less happened accidentally, I would say. So I only started doing the medical research after coming to Guelph, which happened in 2016, because Guelph really gave me the freedom to expand my research, like in a more free way than I experienced that before, right? So I knew, okay, I am a nuclear physicist, a nuclear astrophysicist, but then we had these ideas about medical research, and the department was super supportive in me trying this out, and attracting also funding to financially support this research. So
well, so let's not get too far ahead of ourselves here, because I want to really explore this journey, because this more so than a lot of others really seems like a journey. So you do your undergrad, you do your grad work, and you're explicitly working with as a nuclear physicist. So
that's right.
Prior to getting into the medical part of this, what exactly is it that you're exploring? What's the difference between an experimental nuclear physicist and a theoretical nuclear physicist? What do students have to look forward to in those realms?
Yeah, so I think Daniel was already on the live stream, right? That was, I don't exactly remember when that was. So Daniel is a theoretical nuclear astrophysics physicist. So he would calculate, for example, what happens inside a star, often using very complex computer simulations nowadays to figure this out. So as an experimental physicist, I'm really mostly thinking about new experimental techniques to measure the things that we are interested in, and then to compare them to theory. So there's a very strong link again between these two fields. We work separately, but kind of the overarching goal is kind of the same. Like there is this umbrella, and we're trying to answer the same question. For example, where do the elements come from? So I need Daniel to tell me which, for instance, nucleus do I have to measure to figure this out? What is like most sensitive, say? And then we can try to measure that in experimentally at a facility, and then we compare, and then and then Daniel would go ahead and refine those theories and say this theory makes sense and this doesn't make sense. So this comparison of experiment and theory is really important. That's what drives us. Right? Yeah. So yeah.
Well, no, that's exciting, because I love that balance, because when I was doing my work with polymer physics when I was doing my degree, and it was one of those things where we were very hands-on and very experimental, and it was all about sort of probing the physical capabilities of these systems. And at the time, there was a lot of experimental polymer physics that was taking place, but I don't think those two fields back in the early 2000s when I was doing my work were as connected as people seem to be connected now. Now there seems to be a lot more communication between theorists and experimentalists and them working together. And I wonder if a lot of it just has to do with how much easier it is now to communicate with each other.
Absolutely. I strongly believe so. Yeah, we communicate a lot with the theorists, especially in our field of nuclear astrophysics, because these theories are very, very complex and we cannot do these calculations. So it wouldn't make no sense if you just randomly pick one type of experiment to do, and then later it turns out it's not an important experiment to do. There's so many atomic nuclei out there, and we can't understand and measure every single detail about every single nucleus. It's really like we have to specifically say, that's the key information we need to answer if heavy elements are made in whatever, neutron star mergers or something.
And as an experimentalist, you also are all sort of, you're vying with other groups from around the world to use just a few key facilities and a few key experiments. It's not like you can necessarily set up a cyclotron here and do the experiments here. You're flying all over the world to do this.
This is actually, that's quite special about the research I do at these, what we call radioactive beam facilities. So maybe let me briefly explain.
Yeah, absolutely. Go ahead.
Most atomic nuclei, some atomic nuclei are stable. Those are the ones we find on Earth, which make our stable elements. But there's a lot of atomic nuclei out there which are unstable and they decay. And it's often we find, so if we are concerned with the question where the heavy elements are coming from, it turns out that these unstable nuclei, we call them exotic nuclei, are playing a key role. Because that's just because in the star, the environment is so special, and so it's also very exotic. It's very hot, it's very dense. There's a lot of neutrons flying around there, and it gives us nuclei which have many more neutrons than they normally have, and that kind of makes them unstable. So what we like to do is to figure out how these nuclei really look like and how they behave in these stars, to test again our theories and our understanding of the universe. The issue is that you don't find these exotic nuclei just on planet Earth. They're unstable. They're decaying in very short time scales, often like just small fractions of a second, like in the thousandths of a second or even less, they decay. So you have very short time scales to work with. So the way that works is that we create this exotic nucleus, which doesn't really exist on Earth. So we create that for, say, a millisecond, a thousandth of a second, and then we study it. And then we try to understand from that how, say, an supernova explosion might work, or some exotic scenario in the universe. So these experiments are very complex and expensive, and there's only a few places on the world where you can actually produce these exotic nuclei for a short time. So one of them is TRIUMF in Vancouver in Canada. And there is a new facility coming up in the United States called FRIP. And there's a second facility at Argonne National Lab in the United States. So those are, I would say, the leading facilities right now on the American continent. And then there's things in Europe and in Japan and China and so on. But there's really only a handful of places where you can do these experiments, where many physicists come together, both experimentalists and theorists working together to do the key experiments. So that's really exciting that I'm allowed to work on these big machines, on these big particle accelerators and detectors. I'm not even touching the particle accelerator itself. That's other experts who do that. They will not let me do that. So it's really so it's nice to work on these large facilities, but the drawback is that you are only allowed to touch your own little thing, which you are the specialist of. So you always need a specialist for each of these subsystems that you need to run your experiment. But that's also great. There's a lot of communication because of that. Yeah.
Well, I was going to say that's probably one of the most exciting things about that is that, you know, you're working within a team and a group of people, and then coordinating with other teams and other groups as well.
Absolutely. That is just, I love that. I am a person who really loves to work with other people, and traveling the world and doing these experiments and meeting people you haven't seen in a while, or just
this is the exciting
Zoom
thing,
conversations with. So that's exciting. That's
absolutely.
really
And
fun.
you know, I think when people might get the misguided idea that if you were to get into nuclear physics, maybe that it's a somewhat solitary thing. Whereas it's almost quite the opposite, where you have to work with these big groups and have to work with these big teams to make any sort of headway.
Yeah, nuclear physics is around for so long. So many people think nuclear physics is kind of a dead field because, well, it started, we all know how it started, right? Fission was detected, and it started before that, right? The nucleus was discovered, and then nuclear fission was discovered, and then bad things happened with that. And like after the war, people made a lot of progress very quickly, 60s, 70s, those were like the classical high times of nuclear physics, where everything was kind of new, and then a lot of things were discovered, and then maybe the field slowed down a little bit. But now with the option of having these exotic beams, there's a huge renaissance, and it's like, I don't know, already now probably 2-3 decades that people are heavily interested in investing into these huge facilities like FRIP in the United States. It's just a 4 hours drive from Guelph, by the way.
Oh, wow.
If the border would be open, but it's closed.
Well, hopefully that'll be sooner than later.
Once the border's open, you should take a trip to Michigan State University, where FRIP is under construction. It's a $1 billion project, and that's the scale. Wow. It's really huge. It's really huge, and it's going to be the world's best facility for doing this research.
Well, and I guess my question would be, you know, we've got these different facilities. You've got CERN, you've got TRIUMF, you got this new one coming up. Are these so, and excuse my ignorance, I don't know a ton about nuclear physics, but are these facilities specifically aimed at having beams that are for specific experiments? Are they always trying to be the bigger, the better one, or are they, you know, to no pun intended, are they targeting specific elements to
That's a very good question, Orbax. That's a very good and complex question, and it depends a lot on the facility. Let me take in this example TRIUMF in Vancouver. TRIUMF hosts the world's largest cyclotron, which is a specific type of particle accelerator, and it accelerates protons, which are hydrogen nuclei, basically. So it accelerates that to very high velocities. And in early days, the experiments people did had a different goal. Like nowadays, they started doing more like what we call high energy physics, trying to understand how particles are interacting with each other, how the proton works, and then all these kind of things. And then later, people figured out that there's more, there's other things you can do with a proton. And one of them is now creating these exotic nuclei. And that's probably what now TRIUMF is used for mostly, is to use this initial proton with very high energy to create exotic nuclei. So if you're interested, the way that works is you stop that high energy proton in a heavy target, like for instance, a uranium target. And then this uranium target, the nuclei in that target, they break into small pieces. And a few of these pieces are these exotic nuclei we are looking for. And then we filter them out in very short time and deliver them to the experiment to study them. And all that works like in fractions of a second, which is very interesting.
Well, I was going to say,
So
I
really
mean,
TRIUMF,
that's the most exciting part, right? Is that this happens effectively instantaneously. So I would
instantaneous.
assume
Like
data collection is a
find
huge
that,
part of this too.
yeah, I mean, I'm doing this now since I don't know, 20 years or more, but just whenever I sit at this experiment and everything is working, which doesn't always happen, but after hard work and a couple of days, finally everything's working, then I'm sitting there and think, wow, everything's working. Like you start what we call it the ion source, where you start just with a like hydrogen gas, basically, or something like that. The hydrogen has to come from somewhere that you accelerate. Then it goes through this huge accelerator, and then it's guided through hundreds of meters of beamline under vacuum to your experiment, and then you create an exotic nuclei, and then that's transferred, and then there's so many things, and then your detector setup is complex, and there's so many people involved. And everything has to work, right? Vacuum has to work, and the accelerator has to work, and cooling has to work. And I still find that fascinating that nothing breaks for a day in this complex machine. I find that so cool.
I think that's one of the joys of being an experimentalist, is actually creating an experiment that does work, because you're always confronted with so many problems. When something's finally working, that seems like the miracle of the science right there.
Yeah, that's the most rewarding moment. I mean, it's also rewarding to whatever, get a grant or do a great lecture. But I think the most rewarding thing is if you have an experiment and you work through day and night to set it up, and then it's working.
Yeah,
that is really satisfying.
So to shift gears slightly, you know, we've spoken kind of to this idea of nuclear physics and of looking at these rare exotic isotopes and elements. Now, it might seem like it's a bit of a leap for some people to say, how does medicine get tied into this as well? But as you even said, you know, X-rays have been linked to cancer treatments for, I mean, my entire lifetime. And I assume some of these other high-speed particles can be linked to it as well.
Exactly. That's exactly the link. So if we talk about TRIUMF, I told you we have this huge cyclotron, which accelerates protons to very high velocities. And it turns out that these protons can be used to treat cancer. So that's something people already discovered many decades ago, but didn't quite have probably the technical possibilities to set this up and really improve things. So, you know, cancer radiation therapy is something that you use in almost about like 50% of all cancer treatments. There's some kind of radiation treatment involved. It's a really critical component of 50% of cancer treatments overall. So it's really important to make it better. And radiation treatment is already very, very good. It has improved over decades so much by just small steps and just making it better and better and better over time. And the goal always there, of course, is that the treatment is more successful, so that you kill the tumor cells with that radiation. But at the same time, you also have to be careful to not cause any other damages, like secondary cancers or other side effects of this radiation, right?
Well,
So radiation therapy,
I guess that's the thing that people don't necessarily totally understand about these types of treatments, is that these particles, when you put them into the body, don't just go and stop at the tumor. They're not sort of seeking these things out like a missile. You're just sort of scattergun shotting these things into the human body.
Yeah, so classical radiation therapy uses something similar to X-rays, just higher in energy. So we call them gamma rays, but essentially it's like X-rays. And you fire them as good as you can towards the tumor. And if there is enough of that radiation dose, that will kill the tumor cells. But the problem is that the gamma ray penetrates the entire body. So you can do some clever tricks to make it that most of it goes to the tumor, but you cannot avoid that radiation dose goes also to other parts of whatever is like in the path of that gamma ray beam. For instance, you always see like these. You get like a burning sensation on the skin, just because there's energy deposited whenever the radiation enters the body.
Yeah.
And yeah, these things can cause issues later down the road. So the interesting thing is, if you do not use a gamma ray for radiation therapy, but instead use a proton, that proton behaves very different. It enters through the skin into the healthy tissue, and it doesn't lose so much of that dose. It's not stopped until it actually reaches pretty much the end of its track. Like that really doesn't make it out of the body anymore. Like that proton really stops in the tumor if you do it right. And only at that point it deposits a lot of its energy, not so much before, and almost nothing after. Like the gamma ray just goes through and it deposits a significant amount in the tumor, but not by far not all of it. The proton is much better in that sense, right?
It's sort of the difference
So
between a shotgun and a dart.
Sorry?
It's sort of the difference between a shotgun and a dart. You know, one just sprays and then one goes and launches and lands in a spot.
That's right. So it's a very accurate way of radiation therapy. And it turns out that in order to do it, the proton, of course, it has to reach the tumor. So you have to bring it, say, 20 centimeters into the human body. And it turns out you need a proton with a lot of velocity, with a lot of energy to do that. And that energy roughly matches what you can get out at TRIUMF of the cyclotron. Actually, that has even more power, but you need a pretty large accelerator, like a cyclotron or something, to do that. So that's really the drawback there of this kind of therapy. So we call that proton therapy. This is this kind of new form of cancer radiation therapy. And TRIUMF is an ideal research facility to explore it and to make it better. So we really use the same machine. That's where that strong link is between medical physics and nuclear physics. It's very interesting.
That's interesting. And I guess, you know, presumably these are just the sort of, I guess you call them baby steps towards getting to first understand that research fully, to somehow maybe create smaller versions of these cyclotrons or get some of these high energy protons to eventually be used. But first you have to know what they're actually going to do.
Yeah, exactly. So meanwhile, you can purchase these cyclotrons, which are targeted towards doing exactly this kind of proton therapy. And that's been done. Like in the United States, there's already many facilities up and running and people get their treatments. Oh yeah, so proton therapy and its other forms of this entire thing is called Hadron Therapy. A hadron is kind of a nucleus, if you want to say so. So there's actually two versions. It's either proton therapy or carbon ion therapy. A carbon ion is similar to a proton. It's the nucleus of a carbon element, so to speak. And you can use that as well. And there's these two types of facilities. And in the United States, it's mostly or exclusively proton therapy, which has been done. But overall in the world, hadron therapy, there have been over 100,000 people being treated. So that's already a lot.
Oh, wow.
Canada is a little bit behind, unfortunately. So TRIUMF used to be the only place where you could receive proton therapy. It's not done anymore because it only could treat very specific types of cancer. But there is a strong collaboration with the US. So if you are candidate for proton radiation therapy, you can travel to the United States and get it there. But so there is things under discussion, and there are plans to build these facilities in Canada as well. So hopefully in the future that will come up, that we have more direct access to this kind of therapy.
Yeah, that's exciting. Now, you also are you know, as an experimentalist, the detectors to these types of things must be I mean, you've got a cyclotron. It's creating these high-speed particles.
Yeah.
You're firing them at stuff, but you still have to be able to measure what's coming off of this, and it has to be measured in, like we said before, fractions of a second. So I assume the technology towards the detectors is always changing, always advancing, and there's a lot of breakthroughs being made there.
Yes, absolutely. So actually, that's more what I actually do as a nuclear physicist. I'm not so involved with building or running a particle accelerator. That's already there, or that's other people taking care about that. My research happens wherever that particle then arrives and say shoots on what we call a target. If we do like a nuclear physics experiment, or if we do medical research, then we usually work with phantoms, which behave similar to tissue. So we shoot that onto something, and then our detectors try to measure what happens. So let me give you an example. for the medical research, what we are trying to do is we are trying to find a way to figure out for the patient, where does this treatment beam really stop during the treatment? It's a very precise therapy. We said the proton really can stop in the tumor, but you really want to make sure it stops where you want it to stop. It shouldn't go a centimeter too far, or it shouldn't stop a centimeter too early, because then the treatment will not be successful and you damage tissue, which is actually healthy tissue. So that would be really bad. So this kind of, we call that range verification, is very important. And there's very little you can do right now to offer range verification to the patients during the treatment. There are some methods to do that after the treatment, but that's not so great because then it's kind of too late. So you really want to make this really ideal and to really push it to what we call like the gold standard. It would mean that you immediately have that feedback from a smart detector where that proton stops. But that's not so easy because you cannot really look inside the patient, right? You actually don't see that proton. You don't see what it's doing. You don't hear anything. You don't see anything. You're completely blind there, right? But our detectors are actually able to measure what is happening if that proton hits the tumor. So that's what we are using. So we are trying to build detectors which are able to tell us where the beam stops with a very high precision of a millimeter or better. And then we're also building the technology to make that fast, to make that kind of an instantaneous feedback, to say, hey, you are off by 2 millimeters, stop this now, right? This is what we are working for. We're not there yet. We are doing baby steps, but that's the long-term goal, to actually build something which can be used in an actual treatment scenario.
Well, and to make something like this, adaptable and on the fly, seems like that would be a huge challenge to actually face.
Yes. So what really helps there is the technological developments of the last years. Computers getting faster, chips getting faster. You have all access to this digital electronics. We would, as physicists, never be able to build this from scratch, right? But the consumer market kind of offers so much now, so powerful devices which we can use, which are so fast in analyzing data. So basically what we have is we have this detector, and it offers us these signals that we are interested in. The question is, how do we analyze that? How do we display that in kind of real time? So then you have to crawl through like a lot of data. There's like gigabytes of data coming to us, and then within seconds we want to decide, is the treatment beam positioned correctly or not? So you need fast detectors, you need fast, what we call data acquisition systems, and you need fast computers, and the market offers these things nowadays at affordable rates, and they are mobile devices. So that's really different, even from my time. Like when I started,
I was going to say the exact same thing. Yeah,
we had like shacks full of electronics, and it was pretty slow. And that was already, of course, very good at the time. But nowadays, you just have like a little desktop thingy which we can take into our hand luggage in the plane. Like we can carry our entire data acquisition system in our plane. We do not even have to ship it. We just go wherever we want and plug it in, and that's amazing.
It's incredible stuff. And it's even like I said, in the course of our professional careers, like this stuff has changed massively. I also want to point out that we do have this opportunity to take questions in real time. So if viewers have questions, we're happy to bring them up.
Yeah, that would be great.
It's a rare opportunity to speak with a experimental nuclear physicist, and we'd love to chat with them some more. So feel free to put them up there, and we'll get into it as well. Dennis, I know that you have you run a group. Your students will actually get an opportunity to sort of work on these things. And my question with this stuff has always been, if you have a student who's doing a master's or who's doing a PhD, it seems to be very dependent on the experiment that they're doing. And these experiments seem to be so highly need to be coordinated. They have to get so much data. What is that like for graduate students?
Yeah, that really depends on the type of research.
Yeah.
So let's say for a nuclear physics or nuclear astrophysics experiment, we often wait a long time to get these beam times to be allowed to do this experiment because we said there's so few facilities worldwide. So often what happens is that if a student joins the group, then I already have a very solid idea of the experiment, or ideally maybe I have already the data on the hard drive for that student to analyze, because the timescales are sometimes so long and also unpredictable. So often the students actually start doing data analysis, which involves some programming. I mean, we do have software packages ready to go to kind of analyze these data and filter out the information that we want. So I would say typically a student would start, of course, doing a lot of reading about the research because it's very specific. So to try to understand what's the goal. That's always very important for me also as a researcher, is to try to always know what's the actual question, what's the research goal here. And I like the student to also have that same understanding so that we are on the same page and we are all excited about it and can talk about it. And then students start analyzing data of an experiment, but at the same time, they start traveling to these experiments if we don't have a worldwide pandemic, and participate in these experiments. And then they learn a lot about this. At the beginning, it's maybe sometimes a little bit confusing for them to see these very complex machines and to kind of figure out what is doing what. But they
and legendary
learn.
machines too. Like, these things are for physics nerds today. I mean, things like TRIUMF and CERN have been part of their entire adult lives.
Yes. But I mean, that is super motivating and exciting for
100%.
Not only for students, also for me to be there and see these machines working. That's just so much fun. Yeah, then students travel with us to these experiments and run experiments and learn how to analyze them and learn how to interpret the data. And so that is what a student usually does. In terms of the medical thing, it was a bit different because we really more started this from scratch. So there was nothing in place. We knew what we would like to do, but that was more a research topic where a student of mine started really at the basic question, is this actually feasible? And then that's my student Eva started that with me a couple of years ago. She's still my PhD student. Hello, Eva. She started simulating this in the computer to see if that's actually feasible. And then we figured out what would work and what would not work. And then we would buy first equipment to do a first experiment. And then you do a follow-up experiment, which is a little better. And you really do these baby steps. So that was quite a different experience also for me. There was also a lot of fun. I mean, both is great. And in the like for the medical physics one, in this case, the student really goes from scratch to ideally the final answering the final question, like is this method working and how good is it? So that's very nice. And in the nuclear astrophysics thing, it's a bit more involved, and there has already been many decades of research there. So you add a little bit, but that's also of course very exciting that you do work with these complex machines. So both is cool. It depends on the student. It depends what you like.
Absolutely. There, we've had this question a couple times with some of our other streams, and it probably bears repeating during this one as well. If you have, are there courses that you would specifically recommend? A young person wants to become involved in nuclear astrophysics or medical physics.
Yeah.
What should they be taking in undergrad that would help them? Are there extra things that they could pick up? We've heard a lot of talk about young physicists learning how to program and getting some programming experience, which is often overlooked in a lot of undergraduate programs for people. Is there anything that you'd recommend that people, sort of have a strong backing in before they get involved?
So yeah, it definitely helps if students are interested in programming and maybe have some first experience. That helps to get them started. The data that we analyze, there's so much. I mean, there's nothing you can really do by hand. So it always runs through some kind of computer program. And if you are able to understand and change the program to your needs, that's already a huge benefit. So if you're interested in programming, then nuclear physics or medical physics is, at least of the style I do it, is always useful. Also, our experiments are so complex that we always kind of simulate them before we do anything. So we
Oh,
ask
okay.
the computer, how does this experiment, how should we set this up? And only after we have done this, we start building the, say, a new detector. Like for instance, we are working on a new detector to do this astrophysics experiment called TISTAR. And that's a very complex device. And we completely simulated that in the computer with a so-called Monte Carlo simulation to figure out how exactly this device should look like before purchasing anything. So because of that, programming and like an interest to work with computers is kind of very useful.
Well, it kind of speaks to what you're saying before of now that there's so much advancements in the consumer sector for these computers. The physicists really have to learn how to use them and how to exploit them to their fullest potential.
Yes. But also don't be scared if you don't know how to use these things. We know that when students come in, they have very limited opportunities to work with these things. You might have seen an oscilloscope or something, or a simple radiation detector, but we know that that's about it. That's all we can offer. Yeah? I mean, we are actually trying, we have discussions to come up with some new cool experiments for the students doing their undergrad research to, like for the lab courses, just to update that a little bit and bring more digital electronics in there so that people already learn as an undergrad student how to use these things. So that's something we're working on. So hopefully we'll, once the pandemic is finally gone, will it ever be? I don't know.
Well, we do have a question in the chat here. This one comes from Samantha. Samantha has a question for you. What are your thoughts on the potential advancements available to nuclear physics coming from quantum computing? Do you feel like there's promise in that area?
I have to admit that I know relatively little about quantum computing. So it has a huge potential, I'm very sure, for theoretical physics in general, so also then for theoretical nuclear astrophysics. Like computing time is always a limiting factor for the research that we do. So having algorithms which can run so much faster like quantum computer promises us, that would surely be a huge breakthrough for theoretical physics in general. But also in terms of, well, we talked about real-time applications. If you can run the analysis faster and more complex, that can only be good. How exactly that can look like in practice, I don't know. But we also, on the experimental side, we are always pushing the boundaries of what's feasible in terms of data rates and speed. So just having that faster, bigger, better by quantum computing would be amazing. But for experimental physics, I'm not exactly sure. I do not know enough about quantum computing to make a decent statement there. But for sure, that's, I mean, super exciting. I mean, if that really fully works. So what I really like and I'm really interested in, it's kind of a word everyone is using a lot nowadays, but I think it's really important. That's artificial intelligence. We see really some breakthroughs on various fields. I think AI is just now slowly approaching that state where we can use it for research, but there have been breakthroughs in mathematics. There have been breakthroughs in the way AI plays games and things like that. But I see a huge potential for that. So we, for instance, have some issues or problems or questions to the way we analyze our data for certain things. So we always kind of try to answer a specific question or get like a certain quantity out of our data. And we are not always 100% sure we are doing that the right thing. There might be better ways of doing that. We know the information we're looking for is somewhere hidden in the data, coded in some complicated way, and we try to figure it out and dig it out. And I think AI could probably do a better job in many, many cases. And I think AI and quantum computing is probably strongly linked. And so this advancement will for sure change the way we do science in general.
Exciting.
And that's going to be super exciting to see what happens there.
I think that's going to be the biggest positive thing to come out of this sort of AI revolution, is going to be this ability to analyze the data that we're collecting now. We're collecting so much that there aren't enough grad students in the world to go through it all. So
That's very true.
we have a question here. Speaking of grad students, undergrad, and coursework, this is a question from in the chat from Ricky Summerlin. The question is this: did you find that the coursework you had in undergrad actually led to your current career? This is kind of was sparked by our conversation before about what undergrads could look for to help them moving forward. Do you find that it's still possible to move around to different fields that are different than the one you started in?
So let me maybe start with the second one because it's easier, I think. Yes, I totally believe that you can always switch. So especially as an undergrad student, if you are done with your undergrad studies, in terms of a researcher, you are at the very beginner level. So then you become a grad student. So you do that for say 2 or 3 years, and then you become a PhD student. And even after your PhD, you are still kind of at the beginning of the field, and then there's many more experience levels to climb up until you are a completely independent researcher. And so there's many opportunities to switch gears and switch fields. So I would say totally after, I would even probably recommend that after your undergrad study, you try something different for a while. It changes, I guess, after your PhD, then you're already pretty deep into one topic. Then it maybe become a little bit harder, like if you go for a postdoc, to change. So it would be good to choose something for your PhD if you want to stay in academia, which really interests you. But as an undergrad student and even as a grad student, I don't see that so much. I really don't. And fields are so all connected and close. Like if you can always switch at that level for sure.
I always recommend, it's one of those things too, to try a bunch of these different ones, because after a 4-year physics undergrad, you don't really know anything in physics. So much of your physics career comes from working with other people and being exposed to new ideas. And you almost have to, the goal should almost be to move to different fields and kind of keep learning as time goes on.
I agree. So maybe to answer the first question, well, as an undergrad student, I was relatively little involved with the actual research, although what changed it, I was a like kind of a summer student thing that was at the University of Cologne, and that was a nuclear physics job. So that was the first time I actually did some research, and like I went to my first conference and things, and that was super exciting. So yeah, I did feel that. I mean, for sure, the what you learn as an undergrad student is really the foundation for everything that you do later. You need everything you learn there, like the classical mechanics stuff and quantum mechanics and error analysis, and all this is really the foundation. And you cannot do research without that broad foundation. It's not even enough. You can never know enough if you want to become a researcher. That's impossible. And then the problem is you get so specific so quickly. So that undergrad level is just the necessary foundation for everything which comes after. So it's super useful.
Mm-hmm. Well, we're getting close to the end of our time with Dr. Muecher, so I want to make sure if anybody has any final questions, we'll get them in the chat now. We'll hit what we can. As we wait for some final questions to roll in, I've got a question for you. And this is a big thing that I see in undergraduate and young people learning physics, is that the move now is for people to go online and to watch videos, to try to learn through, videos. What is your what do you find? Are you videos? Are you a book guy? Are you old school, sitting down with paper and pen? What's your move?
I could talk about this for hours,
I know. I don't want to. I figured it's a big topic to bring up in the last couple minutes here, but
so
personally, I think that videos are a great advantage for elucidating things, but difficult to get right down into it.
Yeah. I always recommend my students, especially first year, read the book. It gives you a level of depth which is difficult to get out of the video. A video is a good add-on. It's a good combination together with a good book and together with a good mentor or professor or whoever teaches your course. That combination, I think, is key. If you only watch a video and don't do anything yourself, you will not learn so much. if you only read a book and you only read it, you also don't learn so much. It's like this combination of reading a book, watching a video, talking to people, go to the lecture, do assignments. And that's really what we try to offer. That's exactly what we actually do offer in, for instance, the IPS course I'm teaching. We have this combination of everything. So we have actually some online tools called Flip It Physics, where you have tutorials about topics in classical mechanics. So students are watching that before coming to the lecture. So they're already pre-exposed with that material. And then they can ask the right questions during the lecture. And in addition, I highly recommend always studying the textbook. It's really that combination. But yeah, there's nothing wrong with videos. I mean, those like the stuff you find on YouTube and other sources is just amazing. The quality that people offer and the amount of effort they put into one lecture. And that's not even something you could do on, like if I teach Monday, Wednesday, Friday, it's very difficult to match that. So there are some videos which are just absolutely outstanding. And by all means, you should make use of that resource, but please in combination with everything else. So that to me is the best way of doing it.
Well, I think that's, you know, to me is really the thing is it harkens back to me of when you used to go through in your undergrad and you'd look at the textbooks and you'd read the example that they give you, but you didn't do the example itself. So you read it, you're like, oh, I know how to do this question now. And then it comes to the exam and you don't know how to do the question because you've never actually done it. You've just seen someone else do it.
Yeah.
And
this
that's
is
my
exactly
worry
right.
with videos.
Yeah, it is. And that's why, for instance, in the lecture, what we do is we do like this, the flipped format where I ask a lot of small assignment questions and the students have a couple minutes to try to solve it by themselves during the lecture. So I'm not lecturing that much anymore. It's more the student doing self-learning, and then in the lecture, we try to apply that new knowledge to questions and see how we solve actual problems. And then at the same time, people, students can start communicate to each other and help each other. So I think that's a great way of learning. That has also changed a lot, I think.
Well, and that's the thing. It's kind of the flipped classroom is not a new idea, but it's exciting to see that it's taken root so much in the last few years. We got a couple last questions that I want to get to. Rami has been very vocal on the chat, so I want to bring in one of their questions. How we might have tackled this to some extent, but how useful is programming for researchers?
It depends on the type of research. For me, it's absolutely essential. As an experimentalist of the type of work I do, I'm 100% sure there's many experiments out there where you can live without programming or you have ready-to-go solutions. That strongly depends on the field. In general, in nuclear physics, particle physics, medical physics, very important. In general, for data analysis of anything, also very important. It's just if you program, then you are more flexible. You're not stuck to what the software offers to you. Say you use Excel or something to do some data analysis or MATLAB or okay, if you use something like that, that's already more like programming. Yeah, I think it's really not only for a researcher. I think in general nowadays, if you work in this kind of field which involves anything with computers, then programming is just like at least some limited knowledge. It just gives you a better idea how these stupid things are working. So
this is the thing is that, you know, we always talk in physics a lot about having your prepared toolbox, and you don't have to be proficient in all these tools that are in your toolbox, but you should have access to these tools in your toolbox. So it never hurts to even have just a basic introduction of programming that, like you said, if you need to get more of, you've at least got the starting point there or know what direction to go in.
I fully agree. And even just having a limited knowledge of programming, just being able to take some data from there and to run it through a loop and modify it, that's already so strong. And it really doesn't take so much to learn how to do that. And there's so many languages out there, like Python, that's what we use a lot now with the students, but whatever language works for you is fine. And that's so powerful. You can answer many questions with these simple programs.
Well, we've got one last student question here from Zarin, who I believe is now a Guelph Physics alum, a recent Guelph Physics alum, I believe. If I'm incorrect, then I apologize. But the question is, Dennis, are you working on any targeted alpha therapy projects? Actinium-225 and some growing interest in recent years. What are some of the current exciting isotopes of interest out there in cancer therapy?
Yeah, very good question. So actinium-225 is something TRIUMF is strongly involved with. So what happens there is actinium-225 is a radioactive isotope, like I explained at the beginning of today. This is one of these nuclei which actually decay, which are unstable. And it's an alpha decayer, so it emits a helium-4 nucleus in this case. And that's a very good thing for cancer therapy if you manage to bring that actinium nucleus into the tumor cell, and then it will decay close, or say you bring it close to the tumor cell. And then it decays, and that alpha particle that deposits then a lot of energy in a very short range, very close to this tumor, and kills the tumor cell in a very efficient way. So the goal is similar to what we do with proton therapy. You bring enough radiation dose into the tumor cell to kill it. So this is more a therapy from inside. So this is something you would inject, and then it's transported to the tumor cell with an agent. And it turns out that this actinium-225 is kind of an ideal isotope in terms of how fast it decays and its energy, and it doesn't emit gamma rays, which are unwanted in this specific case. So that's kind of the ideal radioisotope for cancer research. The problem is to produce it. It's not available on Earth, but in a very similar way that we study these exotic nuclei to understand how stars are working, in the same way we can also produce actinium-225 at TRIUMF. So I'm not directly involved in this research. I'm interested, I'm reading a lot about that. I have colleagues who are working on that, but I am myself not involved with actinium research. Maybe that changes one day. But it happens all at the same place. It happens all at TRIUMF. It might just be the beam time right after my beam time of people trying a new way to harvest more actinium-225. There's not enough of that isotope by far to treat every patient who would actually need it. So yeah, that's a very exciting research.
Well, I think we've probably approached near the end. We've got our classic closing question that we'll do in a few moments here. But before we get to that, I wanted to thank you, Dennis, for joining us tonight. We could clearly talk about this for another 2 hours, but I don't think we want to put our viewers through that. I guess the question is there anything, if students wanted to follow up, is there a website that they should follow of your work? Is there any way that they can follow the research that you're doing and your group is doing?
Yes, absolutely. I mean, I have a website at the University of Guelph, so you can check out some research links there. My office is in McNaughton, second floor. My door is almost always open, so you can always just come and chat with me. I'm honestly really happy if you just drop in and say, hey, I just want to say hello. I want to meet you in person. I want to chat about your research. That's actually my preferred way. And yeah, just contact me. My email is on the website, of course, as well. Just fire off an email if you have specific questions. We can chat on Zoom, whatever. Yeah, my door's open.
Fantastic.
Not right now, but otherwise.
well, that's great. So this is our classic closing question, and it was brought to us originally by our former roving reporter, Mel. She used to join us, but she has moved on to larger pastures, but we're still using it because it's a great ending question. And the question is this.
I'm excited.
What's been your most exciting day in your research career?
Oh, wow. That's a hard question. There's many exciting moments, but I think it's actually in line with what I said earlier, that finally having a successful experiment after trying hard was one of those. I'm specifically thinking, we had this one experiment at TRIUMF where we tried out for the second time a specific idea we had about this proton therapy, about trying to figure out where the beam stops. And that was a serious effort. We bought new instrument. I had 2 PhD students involved, setting everything up over weeks and months. And we had 2 days of beam time, or basically 2 nights. Like during the day, the facility was busy, and so we measured more during the night. And the first night was pretty much a catastrophe. It's a very demanding research environment where you work at, like experimental environment in this proton therapy business, because there's so much radiation produced, and the detector wasn't able to handle it, and we couldn't see what we wanted to see in the data. And that was very discouraging, and didn't sleep so well that night. I was kind of puzzled. There were too many problems and didn't look so great. But then in the next morning, we just made a good plan and say, okay, that's what we need to do here. So and then we were able to fix the issue with the detector and the data acquisition system, and then we found a better way of arranging things. And then finally in the evening, it would then start to work, and we could see the signal, and the signal was actually beautiful. It was even better than I thought. So this changed from being kind of depressed about the first try to being super happy that it's actually working that great. So that moment, seeing this finally working, what we were hoping for, was great, because we kind of started this from scratch, really, from the simulation idea to a first experiment, and having a second experiment, and then that first night being somewhat discouraging, and then finally it was working, and it was working better than we had hoped for. So I think that was super cool.
That's amazing. Well, thank you so much for sharing that with us, and thank you so much for joining us and the viewers here tonight.
Thank you very much for having me. I'm very honored to be the first live stream speaker this semester. It's so exciting.
Fantastic.
I hope everyone had a great time out there. I hope everyone's staying safe. And yeah, thank you so much. Thanks for organizing, Orbex.
It's all good. All right. So I guess it's time to sign off. I wanted to specifically not just thank Dr. Muecher, but also thank you, our viewers, for joining and supporting us. As Dr. Muecher said, we will be continuing this throughout the semester. So usually about once a month or every 3 weeks or so, we'll be having continuing our Guelph Physics live stream. So if you don't already, then please give us a follow over on Facebook at Guelph Physics, on YouTube at Guelph Physics, or on Instagram at Guelph Physics. You can find us through all those avenues, and we will see you on the next stream. Stay safe, stay vigilant, and until then, have a science-tastic day. Take care, everyone.